I'm jealous. I have no whip. I have no tag team partner. Everybody's still asleep after lunch, but I have some tiny robots. So, but you have to wait. All right. Complexity in the natural world is fascinating, don't you think? Look at this termite mound. Just look at it. It looks like a Gothic cathedral or maybe a Gaudi church or something like that. But nobody designed it. It was built by thousands and thousands of termites, all acting individually, working together, following simple local rules. No architect. All they know is to carry a grain of sand and put it on top of the grain of sand that they detect in front of them, follow a pheromone trail, and you get something like this. Wasp Nest is sort of the same way. It's kind of neat looking. It looks like somebody designed it. It certainly works well for wasps, but nobody designed it. Wasps are carrying a little specific cell working on these very simple local rules. The nest itself, although it looks designed, is just an emergent behavior that happens automatically on its own. Cities, too. It's tempting to look at complex systems, emergent systems, and think that somebody's in charge, think that the lead bird in a flock of birds is in charge, making the V, but nobody is. Cities are an emergent phenomenon too. They're architects, planners, designers, politicians, but nobody's in charge. The city itself sort of grows organically over a long period of time. When I talk about complex systems, I mean a system that's comprised of lots and lots of little independent elements, all acting on their own agenda. And usually complex systems have emergent behavior. When you step back and blur your eyes, you say, oh, wow, look at this ring nebula, it's awesome. But it's just comprised from billions and billions of dust particles, all obeying laws of physics. So I think it's really important, terribly important, and a vital critical thinking skill to be able to look at complex systems and look at both the individual level, look at both the cyclist trying to gain the most aerodynamic advantage, and also be able to step back, blur your eyes, and see the peloton that's in a line in this formation. Right? It's vital for critical thinking to be able to see both the forest and the trees, to be able to see both the individual person and society. There are people out there that don't believe in the theory of evolution, because a system like life they think is much too amazing to have happened on its own. They think it must be designed by somebody. It's another matter altogether. I'm interested in complexity. Flock of birds. I'm interested in complexity because it underlies all of the world's biggest problems, as we've seen in a couple cool presentations today. War is not, we'd all like to avoid war, even people fighting the wars, but it just sort of happens from all of the local interactions of policyholders and people with their own agendas, and results in armed conflict, like little boys. Economy is another good one, but of course climate change. These are all big problems. We're having a hard time solving them. We can put people on the moon and make smartphones, but we can't solve climate change because most of us can't really look deeply at all of the factors that cause something like climate change. It's not so simple as saying everything needs to be 60 miles per gallon. It just doesn't work. The world's a much more complicated place. Coincidentally, designers are pretty good at solving complex problems and working within complex problems. Brian Lawson said that designers are the people that can go ahead and carry on a bunch of competing designs and solutions to complex problems in their heads all at once. We can't look at things in terms of black or white or good or bad or red and blue. We have to look a little bit deeper. And how do we look a little bit deeper? There's a science of complexity. There's a huge, big, ugly science of complexity with lots of Greek letters. It's rarefied, it's abstract. Nobody ever sees it unless they're doing a PhD. So that's one way we can look deeper into the science. We can try and take systems apart, or we can start from the bottom, and we can build little toy systems and play with complexity ourselves, and hopefully gain some intuitions about how emergent behavior can arise from lots and lots of interacting elements. This is a game. This is called the Game of Life. And it's played on this grid. It's a 0-player game, and it's iterative. Nobody plays it. We just watch it happen based on initial conditions. You guys have seen this. There are 2 rules that run this system. I'm not just showing you a couple of images. I'm showing you an automatically generated script that happens from these 2 rules. There are all these cells. White ones are dead. Black ones are alive. And the 2 rules that govern the game are that dead cells if 2 or 3 of their neighbors are alive. On the next iteration, they become alive. And alive cells, if exactly 3 of their neighbors are alive, on the next round, they become alive. So we watch the game play out, and this shape becomes this shape, and on the next iteration, it becomes this shape, and it keeps going. We've got an oscillating shape. We've never programmed oscillation. We've never asked it to oscillate. The oscillating shape just sort of emerges from this simple set of local rules. There are lots of cool systems like this. NetLogo, StarLogo, we've heard of a few of them. People have made great strides trying to let kids build their own little models of complex system and gain intuitions of how emergent behavior happens, but they're all on the computer screen, every single one of them. And for me, the computer screen is swell, but it's a little abstract. It's a little too pixelated. It's a little too fantastic to be able to pull lessons learned and bring them out into reality. I mean, honestly, I just don't really like screens so much. This is the game of life played out to something a little more cool that really does show some emergent behavior, more fancy than oscillating. So instead of the screen-based system approach, at Modular Robotics, we're a little startup in Boulder, Colorado, we're trying to make thousands and thousands of tiny robots. So this is a system called Cubelets. It's a bunch of these little magnetic cubes. They're fairly durable. They snap apart. It's a robot construction kit for kids. Okay? A bunch of these little cubes with magnetic connectors. Each one does something different. Each one has a microcontroller inside of it. And depending on how you snap them together, you can build little robots before you learn how to program, before you learn about electronics, etc. The black cubes are sensor cubes. Light sensor, touch sensor, sound sensor, motion sensor, distance sensor, humidity, temperature, anything you can imagine. The clear cubes are action cubes. They're like the outputs. They do things. And all of the colorful cubes in the middle are thinking cubes. They're little bits of intelligence that let you build robots that you want. So let's see. Every robot needs a battery cube. And this is one action cube and one sensor cube. This is just sensing twist. So simplest possible robot you can imagine, senses my twist, sends a value to the bar graph block next to it, and the bar graph lights up. But it's modular, so you can take that off and put on a light sensor block. It's nice and light in here, but if I start to cover up the light sensor a little bit, the bar graph goes down. Okay, I'm showing you the bar graph because it's easy in a big auditorium, but we can add a flashlight block that does the same thing, cover up the light, the flashlight dims. We can add, a rotating block. We can even put the flashlight block on the rotating block, and when we cover up the bar graph block, everything slows down, and when we see some light, it speeds up. We can pop on maybe a distance sensor block instead, and we can get something to work when it detects objects in front of it. And the colorful blocks are the fun ones. Pink block's an inverse block. If we put this one in between, then we get the opposite behavior. We get an active little robot until it detects something, and then it slows down. So simple little building blocks of intelligence. Maybe we want to take off some of these things and put on a little drive block with a motor and wheels, stick it on the table, put a distance sensor block over here and a battery block on top. And then I've created the same thing, robot responding to distance, but instead of lighting up or flashing, it scoots toward my hand. I can flip it around like this and it'll scoot away from my hand. That's sort of emergent behavior, but I'm going to try doubling that and adding, let's see, a second little drive block here and another distance sensor block, and I'll put the battery on top. And now I've got a robot that steers away from my hand. Okay? Nobody's programmed steering. We haven't told it to steer, but a steering behavior, simple little insect-type rat behavior, just emerges from the way I put together simple components that I understand. Cubelets are intended to be really low threshold. 4-year-old, 5-year-old can just snap together cubes and play, right? But it's also kind of high ceiling. So I can reprogram cubelets. Everyone has a microcontroller, so we can go in and we can snap on a Bluetooth cublet, pull it up on our phone or on our tablet, see all of the cubelets in our robot, double click on one, see the source code that it's running, modify the source code a little bit, flash it wirelessly. The robot turns purple and shuts down for a minute, and we can see how changing one little element of a complex system can have a ripple effect and change the whole system. So like this flashlight block, I reprogrammed last night. And let me hook up one regular flashlight block that I showed you, and a distance sensor block, and this flashlight block. And I've reprogrammed this flashlight block to be an automatic paper towel dispenser. So when it detects a peak, it turns on, and when it detects another peak, it turns off, just like a toggle. I've reprogrammed this drive block here to listen to these two distance sensor blocks on the end, and whenever it catches a signal, to flip direction and listen to the other distance sensor block. So, basic robot programming for kids, making emergent behaviors, playing with their own little complex systems. But we're just playing. We can play with that all day long. My clicker. Whoops. We're playing. This can all teach us practical stuff, too. I know I'm just playing with complexity, but there are all sorts of things we can really, really learn with this. So, for instance, our entire digital world is one giant, complex, adaptive system. And if we want to prep kids for careers here, we can learn about networking and technology and communication between different devices. Computer networks are boring, though. This is really cool. This is a visualization of my social network on a networking site. And the intelligence built into this map has been able to color code things and put all of my contacts and friends into little boxes by colors. It's hard to work in systems like this if you don't understand complexity. And I'm still not sure what cyber learning means. But complexity and lots of tiny robots are the basics of cybernetics, the study of control and regulatory systems. And cybernetics is the basis of every modern science that's gotten a new journal in the last 20 years. So those are some specific learning objectives. We can pre- and post-test on a lot of them. We can even make them fit within the National Science Education Standards. But really, seriously, building stuff out of complex systems, giving kids the ability to build and manipulate their own complex systems, can give them powerful intuitions about how patterns emerge, about control and dependency, and how the world really works. You know, it's 2012. We don't need a bunch of facts. We need kids to be able to process all of the information that they're receiving, make a thoughtful analysis, and design solutions to problems in complex domains. Thanks.